welcome back. This is the Tutor Wizard. Please subscribe and we'll send you notifications for all of these videos. This is lecture 7 of Math 120 or linear algebra due to the COVID isolation scenario. What we're going to do today is we're going to look at, this is basically the last push. This will be the cutoff for the final exam in my sections, and roughly for the other ones, Dr. Solomonovich, if you're watching from his sections, this will be roughly what it is too, which means we probably won't do eigenvalues, eigenvectors. I may mention them because I really like them, but they won't be on the final exam. So this is the last push, kitty. Stop it. What are we going to do? Linear transformations again one more time. The standard matrices one more time. I'll recap from what we did last time, and then we'll do composition of transformations. And one other thing we're going to do, I'm going to squeeze in there, we're going to give you a demographic of operators on R2. What do we mean by that? Basically, we're going to look at a bunch of linear transformations from R2 to R2, and then look at their standard matrix, and then we'll look at composing a bunch of those things and moving things around on the plane. You can also do this for 3 dimensions and higher dimensions, but for this class and because of the time restrictions, basically what we're going to do is just, I'll do a quick demographic of some of my favorite linear transformations of the plane. Here we go. First of all, let's recall what we did last time. Last time what we were doing was I showed how to define and compute the standard matrix of a linear operator. First of all, we had a theorem that says if you're a matrix, I could define a linear operator. You just define T of X to be A times X. And then if you have a matrix, you could create TA, which is the linear operator from a matrix. If you have a linear operator, you can create a matrix A, which is called the standard matrix of that. And we saw that the last thing we did was I showed the way that you can compute this just cleverly by trying to view it as matrix multiplication. You have to set this one up as m by n and this one by n by 1, and the inside indices match, and then you get it equals m by 1 vector. Or you can set up and you can cook up what that is. Or what we saw last time was, the last thing we did was I stated a theorem that says this is always generated by looking at, and here's the fancy words, I look at the columns of the standard matrix are the images of the canonical basis vectors under T. What does that mean? Let's write that down one more time. Theorem. If T goes from Rn to Rm, is a linear transformation, then the standard matrix of T is given by T, which is the matrix now, which I'm just going to call A, and that is given by T of E1, column T of E2, column ... column T of En. Where what? It's like, who are those guys? Where EI equals 0 ... 0 1 0 ... 0, where is he got a 1 in the ith spot, are the canonical basis vectors of Rn. So you got this collection of E1 to En. They are I and J and or I and J and K in 2 and 3 dimensions respectively, but these are the generalization of the basis vectors of any dimensions. Every dimension has a basis. In particular, you can always find this canonical basis where you have these guys where each vector's ith spot is a 1, everywhere else is 0. They're actually an orthogonal basis. They're the best kind. Let's try that one more time, and then we'll move forward, and we'll do composition of a bunch of these things and see what happens there. But this is what the theorem is saying. It's often easiest to find what the matrix is by just looking at what happens to these guys in n dimensions. Example, T from R2 to R2 is given by T of x1, x2 is equal to another 2 by 1 column vector, which is going to be, let's call it x1 plus x2. This is some kind of shear force with scalar of 1. Either way, it doesn't really matter right now. 1. These are the nice ones of what you want on the exam. I'm being nice to you. I don't make you decide. I tell you, and then you have to show. Don't tell me, no, it's not linear. It is linear. Show it's linear. Don't try to argue that it's not. Trust me, it is. Absence of proof is not proof of absence. Show that T is linear. 2. Find the standard matrix T of T. Again, the books are technically distinguishing between the two objects. T is the operator. The matrix is this is the standard matrix of that operator. And this is classically on one of my final exams anyways. This is classically what you should probably expect, or each time it'll say decide. I might be mean. It'll say decide if it's linear or not. The ones that are linear, find the standard matrix. That's what's going to happen every time. If it's linear and has one, we want you to give it. The theorem says it's not that bad. You just look at what happens to E1, 1, 0, and 0, 1 here, and you'll get the standard matrix. Solution. 1. Again, that's bad. A and B. So A, because I want to use 3 axioms, I use I for this indexing. 1, what should you check? This isn't technically one of the axioms to be a linear operator, but it's the best way to check that it's not. Where are you going, sneaky? Oh, there's a cat hiding behind one of the lights, and now I can't get her. She's just going to be in there messing with stuff. You'll see in a second. I'm going to put this down and catch her when she comes out. 1. Check if 0 goes to 0. T. Oh, she got away. T of 0 is 0, 0 plus 0, which is 0, 0. So 0 goes to 0. I don't say therefore linear, but I'm on the right way to showing that it's linear. If that had not been true, either I made a mistake or it's not linear immediately. Kx. Every time I have to do this. Kx is kx1, kx2 for an arbitrary vector in 2 space. That means now that when I apply t to that, t of kx is equal to t of kx1, kx2, which is equal to what? This is the definition of what t does. Now I put that, this is just like evaluation in calculus with one variable. I put this wherever there was an x1, x2 in this expression. So this becomes, in the image, the first coordinate kx1, and then the second coordinate is this plus this. So this plus this, kx1 plus kx2. There's a k in both of those, so I can factor that out. That is kx1 times k, using the distribution properties of the real numbers in reverse. I have k in both, I can take it out. Kx1 plus x2. Now I see I have k in both coordinates of this vector, so I can reverse scalar multiply in reverse. So this is k times x1 plus x2. And who is that? T of x. So it spits out scalars. It doesn't like scalars, apparently. It spits them out. What's our third condition? Every time I need x plus y in 2 space, and then I have to see what t does to that. So first in my mind, I look at what kx looks like in the space I'm given, and then I look at what x plus y looks like in that space I'm given, and then this is going to be, what is this going to be? Technically this is x1 plus x2 plus y1 plus y2, which is equal to coordinate-wise addition. Every time I have to do this. No, that's wrong. Don't talk and annotate at the same time. x2, y1 plus y2. You have to do this every time. I have to see what happens to scalar multiplication and addition. So guess what I'm going to build every time I try to show that it's linear? This thing and scalar multiplication. Now once I built this, now I'm going to move this guy with t. See, what's happening is I have 2 points in space, and here's the origin. Oh, so that I'm technically creating, you can view them as vectors, these points. I'm moving these vectors around in space, x and y. But geometrically, to add these, I have to go tip to tail. So he has to go and do this. And then this is x plus y. And so then I have a new point, this guy. And then I'm moving that with t. Then I'm going to move this point somewhere else with t. So first it's asking when I add them in R2, and then I apply t. Is that the same thing as applying t to x and applying t to y and then adding those after? This is what we're doing in this construction, the 2x2 definition of geometric vectors. It's asking if I add these vectors in 2 space and create x plus y, this guy, and then move it with t, is that the same thing as moving x with t and moving y with t and then adding them? And yes, it is, because it's a linear operator. So now I apply t. T of x plus y is equal to t of this guy, x1 plus, it was right the first time. What was I doing? x1 plus y1, x2 plus y2. When you do coordinate addition correctly, coordinate-wise, that is hard. So then I have x1 plus y1, x2 plus y2. What's that going to do? Now t says it does, I put this wherever this was. So it takes the first coordinate and just places it back there. And then it takes these coordinates and adds them. So then I have x1 plus y1 plus x2 plus y2. Then I just group the x's together and group the y's. Yeah, just go through the motions. If this is linear, it'll just magically fall out. Group the x's together, group the y's together. This is the vector x1 plus y1. And then I group the x's together, associate, use all the rules one at a time. This is x1 plus x2 plus y1 plus y2. The axiomatic rules of rearranging numbers never changes regardless of what mathematical subject I'm in, because they're the 10 axioms of how to move around numbers. Now what does that give me? Can you see now in reverse that this is addition of 2 vectors? There it is, this one plus this one. And that's what I'm seeing in reverse. This is the addition definition of vector addition. This one plus this guy. And who is this? T of x. And who is this? Well, if I put y there, it would be T of y. So T is linear. To show it is a mammal, you have to check all the axioms. You can't just be like, oh, it had 1, therefore it's a mammal. It's like, no, careful, you'll get platypide. A platypus is awfully close, but he lays eggs, so not a true mammal. If you want it to be linear, check all of the axioms. Therefore, it's linear. Now what? Now I'm going to, because it's linear, it has to immediately have a standard matrix. B, the standard matrix. I'll do it both ways just in case. I find I like one version more than the other, and at first I find a lot of people do. What is that saying? If I'm going to view T of x as AX is what it's saying. I'm viewing whatever's happening here as matrix multiplication is what they're saying. So instead of saying T of x equals this, I'm going to say AX equals this. And so what that's going to do, I'm trying to turn T into an A. So I'm trying to say AX is going to equal this thing. So A times what is X in here? This is an arbitrary X1, X2, which is 2 by 1. And I want that to equal X1, X1 plus X2, which is also 2 by 1. That's what they're saying. They're trying to say, can you turn T and view it as multiplication on the left by a matrix? Now that I have that, I can say, well, what's this? You can immediately see this game actually tells you enough information to tell you what the size of A has to be. Because matrix multiplication is only defined when the inside indices match, and the size will be the outcome. So what does this say? A has to be what? 2 by 2 in this case. I'm going from R2 to R2. That also tells me. But it has to be 2 by 2 so that the inside indices match, and the size will be the outcome. So now I know that I can play that game intuitively. I don't need a bunch of fancy machinery to see that that's now the size of the matrix I would need. And now This is exactly what we're doing, and I showed in earlier videos when we do matrix arithmetic and algebra, when I define matrix multiplication, this is why we define it this way, because what is this outcome? It's this row dot product this column. So I have to do finger this one, and what do I want? Just an x1 and no x2s to get this. So I'm going to get a 1 and a 0. And then for this one, I need one of each. So I need 1 x1 and plus 1 times x1, so I'm going to get 1, 1. This says that the standard matrix of T, which they usually just call A, is going to be 1, 0, 1, 1. If you don't like that or you want it, now let's see either way, whether you like it or not. I'm going to show you and match with this example, which is what you should be trying to do. Once they give you a theorem, you need to take an example and see where all the A's and B's and C's and K's and M's and L's and whatever the hell they gave you in the theorem, where they fit in the problem, and see what that's saying to us now. So the theorem tells us that T will equal T of E1 column T of E2. And you're like, yeah, you said that a few minutes ago and it still means nothing to me. So here's where we flesh in the meaning for that thing. What are these guys first? Who's E1 and E2? I'm in R2, that's 1, 0 and 0, 1. IJ is actually who they are. Then what does it mean to do T of this? I know what T is, so we'll put 1, 0 in there and see what happens. We'll put 0, 1 in there and see what happens. Then that is the matrix. It's not that bad. Let's do that. Coffee reappeared. That'll happen periodically. Mathematicians turn coffee into theorems. What we're doing, part 2, my second proof of, or showing that my second method of computing the standard matrix. E1 in this scenario, I'm in R2, so we'll try to for the rest of it, and when we do our demographic, it's going to be operators, so they're going to go from the same dimension to the same dimension, R2 to R2, but it could be R2 to R3 or R2 to R1 or any of these mixings. So you have to say in your domain, what's your basis canonical vectors? I'm in R2, which happens to be the same in my codomain also in this case. Who is it? Also, is that too much? He's I in this one, 1, 0. The vector we were calling I in 2 dimensions. And then who is E2 in this case? J, it turns out the J vector, who is 0, 1. You didn't have to put the I in the J if you don't like that. Magic. Gone. So E1 is 1, 0 and E2 is 0, 1. Now let's see what T does to that. What does T do to that? Well, T of E1 is this guy, T of 1, 0. And it says I copy this out, 1, and then I do 1 plus 0. And that gives me 1, 1. What's T of E2? T of E2 is T of 0, 1, which is, it says you copy this guy out, and then you do this one plus this one, 0 plus 1, which is 0, 1. That tells me that the standard matrix is T of E1 column T of E2, which is, now you can see this is the first column 1, 1, and this is the second column 0, 1. This is the standard matrix of a linear operator. 2 ways of computing them. I've given you more than enough rope to hang yourself. Just don't do that. I'll give you a gun and I'll give you a knife. Pick your poison. Just be careful. All right, now we've seen that every linear transformation has a standard matrix, and every matrix you can define a standard or a linear transformation, so they're interchangeable. But more importantly, on an exam, we're going to give you a transformation. We're going to say, is it linear? If it is, find its standard matrix. Now we have a way to do that. What we also want to now start doing is composing more than one linear transformation. So we're going to do, I really want to say it, but there's always one more. There's always more statements. Trust me, there's infinitely many deductive statements I can make, declarative statements about mathematics, and that game never ends. The same cat just knocked over a bunch of Lego. Yeah, this is the one knocking everything over. You want to climb the wall? You don't want to do it now? You should see when, there's no camera. She just likes to magically climb walls. It's weird. And then there's a camera on. She's like, I'm nervous. What's going on? We're trying to shoot videos. Can you just back it out for 10 more minutes? All right, good. Petra, everybody. Petra. What the heck were we doing? Composition of transformations. This is going to be the same for, and I'm going to keep the composition to R2 to operators on R2. So abstractly, you could do this in higher dimensions. What they're saying is, in calculus, they say you've got A and B and C. And F is going to go from A to B, and G is going to go this, and we're going to do Gog and Foff and all these ones. hog off. Watch the other videos on composition. If we do composition of functions, we do this. We've got like, oh, we say here's an f, and we write a, b, c, and then we have another g, and then this guy is going to be g following f. And so it's cutting out the middleman. I don't need you. I'm going to cut him out. And so then I can just get from A to B. No, we can't really cut him out. He's an intermediate universal serial bus because he has to be the connection between this. But it's a way of connecting from A to C through this. Composition of functions. You're like, why are we talking about that? Transformations are functions in just higher dimensions. So now ABC becomes what? Rn to Rm to Rl, say. I don't know what the dimensions are. Again, I'll take it easy and just picture in your head, we're going to do n, 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 but they could be different, and we're even going to pick n as 2. So 2, 2, 2. Can you make those, watch, can you make an n into a 2? Yes, I can. Can you do it 3 times? Yes, I can. So we're going to stick to R2. So now you can see this is the plane. I'm going to move a copy of R2 to a copy of R2 to a copy of R2. And we don't call them F and G. What did you call me? F and G. We call them T and S now. T and A. I really want to call them, but T and S. So now this is what we're doing. Now you have a vector X. You pick it up. What does T do with it? He puts it in the grinder and makes coffee. Then you drink it. Now, what's the end of that story? Later on I had to go to the bathroom. S is that operator, I guess. They're both linear. We'll see. Then what does that do? It takes it here. Still a copy of R2, but it moved it around. I'm moving points. Operators are moving points around in space. It took it in the first copy and it moved it somewhere. Where? Horribly, we have to write it like this, T of X. Then you forget that symbol just means a point in space again. Y, we call it. Y equals f of x. What did I do with a regular function? I took a point and I moved it around and on the line, real number line, and then we draw the picture of that and you get a graph. These are hard to draw because they're multi-dimensions. Now what do I do with that? Well, I'm going to pick that point up and move it with s. What is that going to do? Well, that's going to do s of t of x. It's going to move it to a point. We're going to call that w probably or something like this. Vector, you're a vector. Sneaky. The line means something, you have to write it every time. Yes, you do. Yes. What does this say? Now I get what? That's following T. So now we just did calculus and linear algebra. Yes, because they're starting to connect. This is when it's exciting. We just parse out classes for you at first. This is what we call linear algebra. This is what we call calculus of variations. This is what we call whatever else you want, statistics. We're trying to figure things out in the universe. Eventually they start coming together and you realize that matrices were linear operators, so I have to talk about calculus or functions. So the scenario of composition of functions is the scenario of composition of transformations. Now, if they're linear, which we're going to assume S and T are, this is the next theorem. What are the 2 questions I just asked by doing that? 1, if T and S are linear, is S following T linear? Yes, it turns out. How do we prove that? It has to spit out scalars, and it has to split sums, and it would be nice if it sent 0 to 0. How else would I show something's linear? I don't know. There are 3 axioms. If I give you something new, don't think there's a new technique. It's something new, and I have to use the same technique to show that new thing is the thing I want it to be. Linear. So yes, statement 1, if you take T and S and compose them, that thing is linear. Question 2, because it's linear, it must have a standard matrix. What is that standard matrix? And we're magically going to see if it's going to be to the left, matrix multiplication on the left, S times T, not T times S. Matrix multiplication is not commutative, and F following G does not equal G following F, and so I would hope that S times T does not equal D times S. These rules have to match because matrices are functions, linear transformations. And so if composition is not commutative, neither can matrix multiplication. Let's do an example. Theorem, an example. Moving points around. Where'd you go? I don't know. Away from you. The away from you function. Is that linear? No, it's exponential. Get the hell away from me. Example. I don't know what the sketch of that looks like. Go away. That's in our next video. You'll see. The monode composed with the exponential function is what that was. No, I said theorem, then example. Basically, the theorem is I'm just condensing in a mathematical form, which everyone hates, what I just talked about with that pretty picture. Like, take it easy with your pretty picture, but with the picture then. What did it say? One, I'm asking in the theorem, and then we have a proof of it. I'll spare you these details, but it is true. So theorem, the two questions I just asked. If S and T are linear operators from Rn to Rm and Rm to Rl, respectively, is the composition S following T from Rn to Rl linear? Yes, the theorem says. And because it is, what is the standard matrix of that? It's multiplication of the original 2 is what it says. Answer. Theorem. Let T from Rn to Rm and S from Rm to Rl, and notice that the codomain of T matches the domain of S, be linear transformations. Then 1, S following T is linear. And S following T goes from Rn to Rl, cutting out Rm. And 2, more importantly, this means that this actually, you're like composition, it's like, yeah, with functions you have to do fog off or hog off and all of these things, and you have to do f following g, and if I have f of x equals x squared, and then g of x equals sine x, and you have to say what's g following f of x. This is g of f of x, which is g of, what did f do, x squared, and then, so now I have these horrible functions. When do I have to, have to put that in there? That gives me sine of x squared. I don't have to do that now. What the statement 2 says is composition. The matrix is, the standard matrix is you multiply the matrices together, and that'll tell you how to move points around if you have a bunch of them. If I give you 7, you just find the standard matrix for each 7, multiply those matrices together. Matrix multiplication is kind of sucky, but it's better than doing this. Yeah, for linear ones, I don't even have to play this game is what it's saying. You never have to do this f following g or fog or goff anymore. I just find the standard matrix of the individual ones, because they have to have one. And S following T is this. T and S, the respective standard, let's try that again, respective standard matrices of T and S, then the standard matrix S following T is matrix multiplication of S on the left by S and T. This theorem is saying it's not that bad. If you want to do composition of more than one linear operator or transformation, all you have to do is show that each individual one is a linear transformation, find the standard matrix of those, and then just multiply the matrices. It will give you the more complicated composition. And yes, of course, we will have the generalization of, if you had a bunch, I'm not writing it out, but if you had a bunch of them, tk following dot dot following t2 following t1 is equal to tk t2 times t1 to the left, all the way to the left, even Beyonce to the left, She doesn't know why, but I'm going to guess it's because she knows that matrix multiplication is not commutative, and neither is composition of linear transformation, so it has to be multiplication on the left every time. On the left. Words I said. To the left, says Beyonce. To the left. I know you'll remember now. Beyonce said to the left. To the left. To the left. Let's do an example. Let T from R2 to R2 be defined as T of x1, x2 equals x1 plus x2, the one we used last time. Let's be lazy. And then S be from R2 to R2, just like I promised. So two operators on the plane. And S of x is going to be defined as this guy, x2, x1. This is a reflection of what the line y equals x in the plane. I'll show you in a second when we do the demographic, but here's the point x. Well, here, actually, if we do, this is the point, our starting point, x1, y1. If I go across this, if this is the line x2, actually in the plane it should be x2 and x1, x2. So if this is the line x2 equals x1, if I reflect across that, I will go to where? Oh, x2, x1. This is how we define inverse of functions. Also, the graph is the reflection about this line, y equals x. So this is a reflection about this line. What happens when I do this shear force in the direction of y, and then I do reflection about the plane? These are actually two standard demographic linear transformations that I'm just, at first I just force feed them to you and make you play the game. But these come from wind blowing on a building in one direction, or reflection about an axis. And what happens if I do that shear force and then do a reflection? What does that look like? What the theorem says is I just look at the stand, they're both linear, and therefore I'm going to find the standard matrix of both of them and then multiply them together to get the standard matrix of doing both of these following each other. Solution. 1. T is linear from the previous problem. Why would I do it again? S is linear. Why? Technically I didn't show it, so I know it is, but I didn't show you and I didn't convince, so let's do that quickly. What should I do? 1. S of 0 is equal to S of 0, 0, which is equal to, I flip those. You want to see me do it again? With 0, so it sends 0 to 0. 2. What do I need? Kx. What does that mean? So S of Kx is going to look like, I'm doing this in my head, I know what that looks like, scalar multiplication. This is S of Kx1, Kx2. What does that do? It flips them, which is Kx2, Kx1, which is, there's a K in both of those. K times x2, x1. Who is this? Oh, S of x. K, S of x. So it spit out the scalars, it doesn't like those. And then 3, S of x plus y. I'm not even going to write it down because in my head I've already built what does x plus y look like? I did in the last example too. X1 plus y1, x2 plus y2, coordinate-wise addition. What is that now going to do to that? That's going to be S of x1 plus y1, x2 plus y2, coordinate addition every time. Which is now what? That goes here, which is going to flip those. That will be x2 plus y2, x1 plus y1. What is that? I'm running out of real estate. This is vectors. I can add them in reverse. So this is x2, x1 plus y1, y2, y1, which is what? I can fit it in. This is equal to S of x plus S of y. 0 into 0, it spits out scalars, it splits sums. S is linear. Check. Now, both S and T are linear, therefore they must have, by our previous theorem, a standard matrix. The standard matrix of T is equal to what? We played the game. 1, 1, 0, 1. Why would I do that again? Go back and use either technique to find this. S I didn't, so I'll re-show you how to do that again. For S, what do? Again, we're going from R2 to R2, so E1 every time in this scenario is going to be these guys, 0, 1, and 1, 0, E2 and E1. E1 is 1, 0, E2 is 0, 1. What do I do with that? What is S of E1? That's S of 1, 0, which is this. It does 0, 1. Oh, it's going to turn E0, it's going to flip them. E2, and then conjugation, complex conjugation, the matrix can be viewed as, yeah, so it's going to be this guy. It's actually about the x-axis, you'll see. It's similar though. S of E2 is equal to S of 0, 1, which is 1, 0. I'm going to write that out because mathematically we like to point this out. So what does that say? That says the standard matrix of S is equal to T of E1, not T, we already did T, S of E1, S of E2, which is equal to, we found S of E1 was E2, and S of E2 was E1. If you don't like that, I just want to point it out. Magic, I can erase it. The standard matrix of S is equal to 0, 1, 1, 0. That's what in matrix form it looks like to reflect about the line y equals x. When I see that now, or you put an A, what's that going to do? Well, that's another linear transformation. I've scalar multiplied by A, because there's an A in each coordinate. That's dilation and contraction in R2, and then a reflection. That's composition of two linear transformations already. This is a linear transformation. Scalar multiplication is a linear transformation. Of course it is. Do you think it splits out scalars and splits sums? Yeah. So the idea is we can start viewing, when it's a linear transformation, I can actually start calling and giving names and giving clever formula to these things. This is a reflection and this is shear force and those types of things, which is exactly what we're going to do last, is the demographic. I'll digress. What is the composition of these things? Drum roll. S following T now. The standard matrix of that is S times T, which is now all of a sudden you were like, it seems like you did all this matrix algebra and made me do matrix multiplication and I never have to do it. Well, now you do. One of the places you're always going to have to do it is when I have to do A inverse B. This is an n by n matrix, this is n by 1. You're going to have to set that up and the unique solution is going to be this. You have to do matrix multiplication. And then here's the other time I'm going to do it for sure on the final exam. I can make you do matrix multiplication and not ask you multiply these right here. Now we're going to do it. 1, 0, 1, 1 was, no, that would be T times S, and that's not what we want to do. That would not be true. It's not commutative. 0, 1, 1, 0 times 1, 1, 0, 1. Now what do I do? I go back and I think to myself, they showed me this for a reason, and math is not like this where I can binge and purge certain pieces of information. I definitely want to use eventually how to do matrix multiplication. This is 2 by 2, this is 2 by 2, the inside indices match, and therefore the size of the outcome is also 2 by 2, everything's square, so it will be. But when you go from R7 to R15 to R8, all of a sudden, whoa, what dimension am I going to? And keep track of these things. I'll spare you in this semester. If you want to see more, I'm going to do videos on the nasty ones anyways, just for fun. 0, 1, 0, 1, 0, or sorry, 1 plus 0 is 1, and 0, 0. This one was the shear force, and then we're saying after you do the shear force, reflect everybody. So what did it do? It reflected the rows. It interchanged the rows. Multiplying by a permutation matrix interchanges the rows. This is extremely useful in Markov chains and stochastic processes and these types of things. This is a permutation matrix. He's his own inverse. S inverse is himself, which is also his transpose. All kinds of fun. Not his transpose. Could it be his transpose? Yeah. What's the transpose? Main diagonals don't move and he's symmetric, so he's equal to his transpose, which is equal to his inverse. That was too much. Those are magical guys eventually too, reflections, permutation matrices. I permuted the rows of T with S is what I did by multiplication on the left. Okay, this is the last push essentially. What we're going to do now is, we know what a linear transformation is, hopefully. We know that they all have a standard matrix. We know how to find these in more than one way. And we now know that if we have more than one of these, we can compose them and that stays linear. And the composition standard matrix is just multiplying them all on the left by the individual standard matrices of the individual transformations that I'm composing. Now I want a demographic of a bunch of fancy names and pictures of what we're going to classically do, and are these processes linear, and therefore do they have a standard matrix? And then I can make you memorize all of these things essentially, and then say on the final exam, first I do a reflection about the x1 axis, then I do a rotation through 30 degrees, then I do orthogonal projection onto the y-axis. What's the standard matrix of that? And then I have to know what the three individual standard matrices are, multiply them together, and then you get the overall composition. We'll do an example at the end explaining exactly that. What's the demographic? I need some coffee for a second. I'll make you watch me drink it. Watch the video on coffee reaching equilibrium. That is at equilibrium temperature, room temperature. 1. Where should we start? Let's start with some nice ones, reflections. Mark Solomonovich likes to, in the textbook, really give you horrible ones where the reflection's about an arbitrary line. Luckily the semester's ended and you don't have to do these homework assignments anymore, and I'm going to spare you having to do it about an arbitrary line. What I'm going to do is reflections about the x-axis, the y-axis, and the one we just did, the line equals y, x, or x2 equals x1. So 3 reflections, not the arbitrary one. So these are the ones you have to know. Anything I list here is something you need to know. Anything I don't list in this demographic, you don't have to worry about for the exam. I'm going to give you transformations in the plane. I don't know what Mark is going to give you. Reflections. The first one we're going to do is about, also I'm viewing the plane always as, I'm calling this x2 coordinate x1. So it's not the xy plane, it's the x1, x2 plane now. So reflections about the x1 axis is the x-axis in regular, this guy. And so the best thing to do with these is, and this is why I do them all one at a time and you get to watch me do it, I'm going to build just from the algebraic picture of the scenario what's going on. I'm going to first build the picture, the geometric avatar, then I want to describe algebraically what t is doing to that point, where does its image go. And then from that scenario, I can see that it's linear, and therefore I'll just make the standard matrix of it immediately. If I have an arbitrary point in the plane, and I always make him in the first quadrant, but it doesn't really matter, but he's got coordinates x1, x2. And if I orthogonally reflect about the x1 axis, where did I go? The x1 coordinate didn't change at all. This is x2. This is negative x2, but the x1 coordinate didn't change. I moved to x1, negative x2. So what does that say? That says algebraically, if your reflection about the x-axis, the algebraic expression for that operator is t, that goes from R2 to R2. And we say this time, t of x1, x2 equals x1 negative x2. It takes a couple of years, possibly you've got like 3 weeks, but you can eventually start seeing when I give you these things, you can see exactly when I give you that, I can see that's reflection about the x1 axis. And what does the standard matrix of that look like? Again, the game we're playing is I want to have a 2 by 2 matrix, which I would multiply by this guy to get this. And so what do I need? I need a 1 and a 0. And then I need a 0 and a negative 1. I'm going to do these all quickly to give you the demographic. If you don't like what I did there, you don't see that, I've given you 2 methods of doing it. Look at what happens to the canonical basis vectors, which is always going to be E1 and E2. Or do the game where I played where you do the matrix multiplication. This is the standard matrix. So this is the first one. I'm going to do 2 more in the reflections category. I have so many categories, you're going to be sick of it. I have like 15. I'll stop at about 8. Don't worry, I got so many categories. Moving points in space. Something we didn't even get to do 3 dimensions. Airplane, yaw, pitch, roll. Dang. I'll make a video anyways. Watch them. This is reflection about the x1 axis. Algebraically, these are the things you need to know. That's what, in algebraic form, that's what the geometric avatar looks like. This is what its algebraic avatar looks like, and now this is what the standard matrix avatar looks like. Same thing. This is saying I reflect about here. This is saying now I reflect about the x1 axis, and this is now saying reflection about the x1 axis. Conjugation of complex numbers. Where does it send this? Oh, it sends it to its conjugate. The reflection about this is complex conjugation. Reflection of your complex number to its conjugate. What? We're not going to do complex variables, but this guy is complex conjugation. Still in reflections. 2. Do the same game. We're going to go about the x2 axis now. About the x2 or y-axis. What's going to happen there? Well, again, I do the same thing. I draw what x1, x2 would look like before I start. There's the pre-image, and then what's it going to look like when I do this operation to it. It says I'm orthogonally reflecting about this, and where am I going to go? Now you can see that the x1 moved to negative x1, and the x2 coordinate didn't change at all. So that says I'm going to negative x1, x2. And obviously, yes, you would hope that this would look awfully similar to the last one because it was the same process, just using a different axis. What is that going to look like? That says, in this case, t goes from R2 to R2. And algebraically, what do we say? T of x1, x2. Also, you'll see in a lot of books, they're just being lazy. They're not writing the of x because they don't want to write the extra brackets. Now that the vector has brackets, you don't need 2 sets of brackets. But nobody ever points that out. We're lazy and I don't want 2 sets of brackets. So t of x, which is this. I'll do it again. Like, stop doing that. T of x is equal to what in this case? Negative x1, x2. Now it doesn't look pretty. And what's the standard matrix of this? The standard matrix is going to be negative 1, 0, 0, 1. Reflection about the y-axis. We'll do one more, basically, because this one's extremely useful. This is how you define inverse functions of the graph of the inverse of a function of one variable. Reflection about the line y equals x. I'll spare you the 4th category. I have a 4th category where we do, how are you going to do that? I'll just quickly show you. The 4th category I'm sparing you of is Mark says, here's an arbitrary line. We just use the line x-axis, the line y-axis, and then we're going to use x1 equals x2. Mark's like, oh, no. Here, and then we're going to reflect about this guy. What do I have to do? Well, I have to create a vector, then I have to do orthogonal projection, and then it's going to be actually the orthogonal complement. I have to create this guy, W, and then I have 2 of them, so that is going to be the orthogonal complement of 2 times the orthogonal complement. So it's going to be 2 times W minus the projection of U onto V, where V is in the direction of X. Well, what? Yeah, so that would be T of X in that case. Would be that scenario. X would have to get projected onto But that's what's going to happen. You have to get reflected about that. So we're doing this process on the 3 easy ones I'm sparing you. So you're welcome. 3. About the line x2 equals x1 or y equals x. Again, what are we saying? I'm drawing the picture what I just erased in the general scenario, but now I know it's the equation x2 equals x1 or x2 minus x1 equals 0. What does that do? Again, we saw, or I'm cheating because I know what happens in the definition of obtaining the graph by reflecting about the line y equals x. If I have a point AB or x1, x2, where does it send it? BA or x2, x1. This is the one we just did in the example. What does that give me? The operator reflection about the line x2 equals x1 is the operator from R2 to R2, which gives me T of x1, x2 equals x2, x1. And that says we saw that the standard matrix is 0, 1, 1, 0. So he's not complex conjugation, but he does reflect. He does a similar process to what complex conjugation does. Good. Those are the 3 reflections. Category 1. There is the 4th category about the arbitrary line. Remember, and we'll spare you. These are the 3 that you have to memorize. Projections. Again, I'm going to give you the 2 easy ones, and then you could also make you do the projection orthogonally onto an arbitrary line. I'm just going to do projections onto the x1 axis and the x2 axis and look at those because those are a fairly good start anyways. 1. Projection orthogonally onto the x1 axis. What is that going to look like? I have a point in the plane, we call it x1, x2. And now I'm orthogonally projecting it onto this axis, and there's my image point. In the geometric avatar, you can see, start drawing pictures. This helps me see, and I can build everything from that scenario. This is where I'm literally, you're watching me do it. I don't understand. I know I never draw the picture. Mark just emailed me and was like, in one of your videos you got the cosine wrong, and he's like, you should draw a picture. It's like, son of a bitch. It's like, I know you should draw a picture. It's like, yeah, it'll never stop. Mark told me to draw a picture. I got a bad boy, and I got a -1 from Mark apparently because he critiqued my video and because I didn't draw a damn picture. Draw some pictures once in a while. From this, I see what's going to happen. The image is just going to go to what? It's going to collapse. X1 will stay, but it will make the X2 coordinate disappear. And so what's that going to happen? T from R2 to R2, who is the orthogonal projection onto the X1 axis, is T of X1, X2 equals X1, 0. What does that tell me? The standard matrix of that, therefore, is, the standard matrix of T in this scenario is what? I need to keep this guy, and I need everything to disappear in this row. So that guy, which is an elementary matrix, is a basis vector for R4 also. This is E4. What? Major Caesar. E1 in 4 dimensions. Anyways, that's what the standard matrix of this guy is. There's got to be some deep intellectual connection there that the canonical basis vector of R4 E1 is in matrix form projection onto the X1 axis. Words. Next, the other projection we're going to do is onto the X2 axis. How do you do that? You add an I, and then you change the X2 axis. You have to rewrite it down. You shouldn't just watch these videos, especially in the linear algebra scenario where you're doing this. Try to take some notes and write down some of the definitions and make yourself a thing for a cheat sheet for the exam or something like this. Passively watching is like, Connor McDavid should have passed it over here. It's like, yeah, well, you try. I'll give you a stick and put you in front of 50,000 people. It's a different game. It's a different game. Projection about the X2 axis now. Well, I started with this point, X1, X2. No, it went too far. That was the last time. Oh, back it up. You went too far. You're going the wrong way. Right there, we're going to stop. Now what did that do? Now you can see X1, X2 stayed the same, but X1 went from this guy to, it moved to 0. From that geometric avatar, I now see the algebraic expression for that is the operator from R2 to R2, which orthogonally projects onto the X2 axis, is given by T of X1, X2 equals no more X1. And then this will be E4 in 4 dimensions. The standard matrix of this will be this guy. And I want no X1s, and I want to keep X2. Good. You pray on the exam, please, that I give you an orthogonal projection. Do you see what it does in multiplying? I would like to multiply and do that one first. They associate. I'm going to point that out when we do this. I'm like, why would I care if I move the brackets? If I have this times 2 other hot messes, and I can do this, holy crap, then that multiplication will, and then I'll do that. Association. Next. More. What was this? 3 comes after 2. Yep. Now, it was a jackass, and now I don't remember what category 3 is. Category 3 is going to be, I'm going to just switch with rotations. About the origin through angle theta in radians, counterclockwise, anti-Greekwise. The Greeks invented this rotation business far before the clock was invented, so to call it counterclockwise is, no, this is the correct way to go. Clocks are going anti-Greekwise, counter-Greekwise. It's, yeah, bull. But okay, counterclockwise. What does this look like? basically what we're going to do with this one is I'm going to cheat it, and this one's a little bit more sophisticated. I'm not going to derive the whole thing because I'm sure you don't really want to watch anyways, but this time I'm going to do the same starting point, but now I'm going to switch to the theorem that says when you have a complicated one, and rotations are linear. Yes, they are linear. How am I going to see this? This one's more complicated and it's got a bunch of trigonometry, and like, I know I already didn't like that on the second midterm when you made me do cos of 5 pi over 2 or whatever. It's like, I don't want to do this kind of stuff. 0, cos of 5 pi over 2 is 0. Any multiple. Anyways. Now what am I going to do? I want to switch to the theorem that says I can look at what happens to T algebraically if I look at what happens to the canonical basis vectors, E1 and E2. So now what I'm going to do is look at that in the picture instead of picking an arbitrary vector, which is a little bit harder to see what happens to it, to find the standard matrix and the algebraic expression. Well, we sort of have to do both. Essentially what I'm saying is, first of all, let me draw both pictures. And I have to do this one and this one. First of all, I want to do what I was doing just like last time. I want to say I do this, but then what happens to that? I'm going to now rotate that to this image. I want to know who that is what we're asking. And I've rotated counterclockwise through an angle theta about the origin. Eigenvalues, eigenvectors of this thing. Who do you think they are? Who doesn't move? Who's the only invariant subspace? 0 is the only eigenvalue of this. Anyways, we don't get to do eigenvalues. I'm now trying to push this point, and what we're trying to say is we're going to move every point. How are we moving points in the plane? We're doing this to them through an angle theta about the origin. Is that linear? Well, first of all, we need an algebraic expression for the t. So this is the geometric avatar. That was easy again. It's like you're going to move to here. It's like I like the picture. Now we have to use a bunch of ... x1, right? And ... x2. And oh crap, trigonometry and SOHCAHTOA, and then it's the image of those guys. I'll spare you all of that, but you can do it. It's in Mark's lecture notes. It's in all the other textbooks. Basically, what's the idea? Instead of doing that, I'm going to cleverly just give you what happens to E1. Where does he move? ... Where does E2 move? That's this guy. He's going to move there to those images. And if I look at those, it's much easier to see what is happening there. In this case, what's now happening? Well, again, we're still going to use SOHCAHTOA, and we're going to use those things to derive this. I'll spare you this even. I'm not even going to show you what happens when you do this analysis. This is essentially what's happening, but the standard matrix of rotation through angle theta counterclockwise is what we're going to call it, is going to be what? It is going to be equal to this one. I'm cheating and I've memorized it, so I don't want to derive. Mark's going to send me another email saying you should have really derived it and you should have drawn a picture. I drew 2 pictures, I just didn't want to derive it. Gotcha. I'm going in reverse. This will be cos theta negative sine theta, cos theta. And what does that say? What that's really saying is what is happening. If I applied that to x1, x2, that would give me cos of x1 minus sine of theta of x2, and then sine theta of x1 plus cos theta of x2. And so cheating, that's what it's saying. If I take an arbitrary point x1, x2, and I rotate it through that angle theta, the image point is going to be this hot mess. When you do the trigonometry of that, you're going to get cos theta x1 minus sine theta x2. That's where it moves using the trigonometry of that. I'll spare you. And then this one is this guy, sine theta x1 plus cos theta x2. And you're like, how would you do that? You reverse engineer and you get the standard matrix from this. Either way, all of that you can ignore, I guess. Fast forward, bit. All you need to know is rotation through angle theta from R2 to R2 is defined algebraically as r theta of x1, x2 is horribly equal to cos theta x1 minus sine theta x2, sine theta x1 plus cos theta x2, and you're like, I don't like, yeah, why do you think we like this? Bees knees. this is the standard matrix. This is all you have to memorize. When I want to do composition of these rotations, now I just use this. Let's actually open that up one more time to show you what that actually looks like. Everyone forgets these are real numbers. It scares you so much, but watch. Theta equals pi over 6. Aha. It could be nice. Pi over 2 or 2 pi over pi. Some of them will die, but I'm going to keep them all. What does that say? Then the standard matrix for rotation counterclockwise through pi over 6 is going to be the standard matrix of cos of pi over 6 negative sine of pi over 6 sine of pi over 6 times cos of pi over 6. Cos of pi over 6 is root 3 over 2. Sine of pi over 6 is 1/2. The one I memorize is sine of pi over 6 is 1/2. Sine of pi over 6 is 1/2. Root 3 over 2 negative 1/2. 1/2 root 3 over 2. There's a half in there. I can see it. Can you see it? And then I say, if I give you that, can you see if I reverse engineer that and I give you that matrix and I say, can you tell that that is rotation counterclockwise about through pi over 6 in the plane? Yeah, once you become a math wizard, you can. That's rotation counterclockwise through pi over 6 radians. 4. Contraction and dilation in R2. Is this linear? It's on my list, so I'm going to guess yes. We'll start from there. Prove it. What does that mean? I'm going to take a vector, or what you're viewing as the point x1, x2. If I view it as a geometric vector, what does contraction and dilation mean? Either, let's do the picture where I've dilated it to grow it or shrunk it. You can see it's still in the same direction. I haven't moved this direction, but it's just moving. Where's the image going? There. Oh, this guy x1, x2 is in the direction of this line, which means he's a basis for that line. If you're a basis for that line, any other vector in the direction of that line can be written as in the basis of that one vector, this guy, which means what? They're in the same direction. They're collinear, please. They're scalar multiples of each other. And that will be the contraction and dilation. If the k is larger than 1, it will dilate the vector. If the k is less than 1 and larger than 0, it will shrink the vector. Contraction and dilation. What is that saying? Where does my image go? Oh, this is almost an eigenvalue problem, isn't it? This is eigenvalue problem. Ax equals lambda x is asking, when I multiply by a matrix, what stays in there? Contraction and dilation gives you an invariant subspace under linear transformations. T from R2 to R2, which is contraction of dilation, is T of x1, x2 is equal to kx1, kx2, which is actually kx1, x2. Therefore, the standard matrix of T is equal to kk. Good thing it wasn't 3 dimensions. Whew, close. K times 1, 0, 0, 1. I'll use a different letter in 3 dimensions. SS would have been bad in 2 dimensions. Nah. KKK. You said it. I got so close. I had to. It was like there. I wanted to do it. Bad. KK, which is what? Dilation is k times the identity matrix. You're just multiplying by the identity matrix, which is essentially just multiplying by the matrix this time is the same thing as multiplying by a scalar. And this is essentially what eigenvalue vector problem is asking us. Either way, this is the standard matrix for contraction and dilation. Last category, and then we'll do an example, and then, yes, the semester's over. No more new material. The last category we're going to do is shear force in the x1 direction and then the x2 direction. Essentially, the matrices will look the same, so I'll explain the x1 direction, which is more important. The way that I like to view this is you've built, as an engineer or something, you've built a building, but now the wind is pushing on it, but it's not pushing equally in both directions. It's only shearing or pushing on the building in the horizontal direction. It's not having any force applied in the vertical direction. So this is what's happening. Again, I have an image point here, and what it's doing to the building is it's trying to push the box over. And so what's happening, that's the image of the box. You get a rectilinear rectangle creating a parallelogram or in the plane because it's pushing the building over. Leaning Tower of Pisa, that's not the problem. How do we describe this mathematically? What that's saying is if I have an operator T from R2 to R2 now, and it's going to be shear force in the X1 direction, what does T do to X1, X2? Well, it doesn't do anything to the Y coordinate. The Y coordinate is not being affected, but the X coordinate is being, the wind is pushing the building in the X1 direction, and how much? It's multiplying it by the X2 direction. This is basically doing the row operation, row 1 plus K times row 2. That's shear force, essentially, if you only do one. So that gives me X1 plus K X2. And now can you play the game? What's the standard matrix of that going to be? It's going to be, I need a 1 X1, and I need a K X2, and then I need a no X1s, and I need an X2. This will be the standard matrix for shear force in the X1 direction. Same business, draw this picture. Rotate your head 90 degrees and you will have the picture for shear force in the Y direction. Basically, let's quickly do category 2 and then we'll do an example and then we're done. Alright, the last push. Shear force, pun intended I guess, the last push in the X2 direction. In the X2 direction, shear force is going to be T from R2 to R2. Again, I didn't draw the pretty picture mark because I just did it in detail for this one. I'm not drawing the other one again. I guess I'm being a little bit lazy. That says T of X1, X2 is going to be what? I was picturing what's going to happen here. Now what's going to happen? Nothing to X1, but X2 is going to go to, if you want to put it technically where they put it, K times X1 plus X2. This is exactly what we did in my first example when I said it was shear force. I made the K equals 1, and that was the linear transformation we discussed. Shear force in the X2 direction. What does that tell us the standard matrix is? The standard matrix of this is 1, 0, K, 1. Good. What I did was wrong with this. Should have the box there, then it moves like this. Then I'm going to move this to here, and then this to here, and then this to here, and then we get the box. What's going to happen to this guy? X1 and X2, and then you set something heavy on the box. Oh, now it's going to shear force in that direction with load. So what's going to happen to it? The image is going to be what? X1, K, X1 plus X2. There, Mark, I drew the picture. It worked out good. Also, that shows you if first you don't succeed, try again. Let's do an example. Home stretch. This is my favorite part, making examples for you on the exam. It could be awfully similar to this one, maybe identical. You can't do that. You create haves and have-nots, and then who didn't watch the video? I don't care. Example. Should we do 3? Let's do 3. It's in R2. T from R2 to R2 is the linear transformation reflecting points about the line X2 equals X1. S from R2 to R2 is an operator that, actually no, let's do R theta is the operator from R2 to R2 that rotates points counterclockwise through, let's be nice to myself, not to you. Theta is pi over 2. I'll be nice on the exam and tell you what the cosine and sine values of these guys are. One of them is going to disappear, which is nice. Cosine will disappear. Finally, let S from R2 to R2 be projection associated projection onto the x1 axis. Find the standard matrix of S following R theta following T. Hog off, S or T. So now that we've picked the order, I could have listed them in the problem too, and be careful, I won't do that to you, but I could have listed the three of them and then said find T following S following R. That's a different order. Oh, that will move you to somewhere else. Composition is not commutative, neither is the matrix multiplication. But now that I fixed it, I said find this one. Now you have to do, what does that tell us? This S following R theta following T is immediately equal to what? The theorem tells us this one multiplied on the left times R theta times T. And you're like, no, there's no brackets. And then which one should I do first? No, not that one. I'm going to guess this one because he's projection and he's going to have a bunch of zeros. Good. Let's compute that. What do I need to do? I need to find the standard matrix of each of these, which are the demographic ones, which you hopefully memorize in the next couple of weeks. And then I give you an exam and then you write these out and then I multiply them. You have the standard transformation matrix of this composition of three things. Or 15. It won't be 15 on the exam. 1. The standard matrix of T was reflection about the line y x2 equals x1, which will be 1, 0, 1, 1, 0. 2. The standard matrix of R theta, where theta was pi over 2, is that one I can just memorize. Cos of pi over 2, negative sine of pi over 2, sine of pi over 2, cos of pi over 2. See how it's nice I didn't give you irrational numbers. You're going to get zeros and ones and minus ones. And that is what? 0. Negative 1, 1, 0. What does that tell me? 3. The standard matrix for S is going to be what? This was orthogonal projection onto the x1 axis. What is that going to do? Again, what's the standard matrix of that? Please, on the exam, if you can't do and you get to exactly right here, I have an audience or you have to memorize on the exam, I'm doing this. I'm saying it was orthogonal projection onto the x1 axis, if I got that right. x1, x2 goes to x1, 0. I just draw myself a picture quickly, and then I remember, oh, it's going to be this. And what's the standard matrix of that going to be? It has to kill the y coordinate and keep the x coordinate. That would be the standard matrix of this. Assuming I remembered those correctly. That this was, I'm assuming that this matrix is representing reflection about the line x2 equals x1. This one is rotation of points through 90 degrees. And this one is projection onto this axis. If I got those all right, assuming that is true, I'll do that on your exams too. If you get one of those wrong or copy it down wrong, if you get them right and do the multiplication based on that, I can still give you credit for the things you did. But I'm pretty sure these are the right ones. Now what does that say? Composing those, I don't have to do any of this following that. I just multiply the matrices together. This tells me S following R theta following T. The standard matrix is S times R theta times the standard matrix of T. What is that going to give me? This is the standard matrix of S, the standard matrix of R theta, the standard matrix of T, and now I multiply on the left consistently if I'm doing more than one. What do I do for this? I find the standard matrix of T. I find the standard matrix for the rotation, R theta. I find the standard matrix for the projection onto the x1 axis, which is S. I now multiply those matrices together. Now you can see you've got 3 and no one gave you the brackets, so what am I going to do with that? You're going to put the brackets in yourself, because when I have 3 things and I have a binary operation, matrix multiplication, now I have to choose. And what association says is, does it matter whether I start at the front or the back? No, it doesn't. And you should be smart and pick the one that has a bunch of goose eggs in it. So I'm going to put the brackets like this for myself. If you didn't and you want to start at the back, okay, but this is going to give me a lot of zeros, and then this will give me a lot of zeros. This already tells me that the whole row of the matrix is going to be zeros, because it has to kill the y coordinate eventually, whatever happened to it. What is this? This is equal to a 2 by 2 matrix times 1, 0, 1, this guy. What's that going to do? Permutation multiply is going to, you'll see, on the right it'll move the columns. What's going to happen? 0, 0, negative 1, 0, 0, 0, 0. And then now I multiply this one. What do I get? I get 0, negative 1, 0, 0, 0, 0, 0, 0. Multiplying on the right permutes the columns. We can use a permutation matrix. This is the standard matrix. S following R theta following T is equal to negative 1, 0, 0. It looks really horrible in the fancy theory, but when you're in 2 dimensions and you know what the matrices look like, a lot of the time it ends up being just multiplying a bunch of matrices with some numbers in there. Please hit the subscribe button. We'll notify you, not in this series anymore because it's the end of the semester, but there's a bunch of other videos related to this topic and many more. I'll see you next time. Have a good semester.